A vessel that easily holds 300 psi from the inside can crush like an aluminum can under just a few psi of vacuum. Internal and external pressure are not the same design problem. Welcome back to ASME Section 8 Division 1 in 5 minutes. Season 2, Episode 2, External Pressure Design and Stiffening Rings. Every formula from Season 1 assumed internal pressure trying to burst the vessel outward, a stress problem, solved directly with algebra. External pressure flips the failure mode entirely. It's not about strength, it's about stability. A shell can be plenty strong and still buckle, collapsing suddenly the way a thin-walled can crumples under a sideways squeeze, long before the material itself ever reaches its yield stress. UG-28 governs this case, and it can't use a simple formula, because buckling depends on geometry, length, diameter, thickness, in ways a single equation can't capture cleanly. So the procedure is graphical, not algebraic. You assume a thickness, calculate two ratios, length over diameter, and diameter over thickness, and use them to read factor of a geometry chart. Factor A then gets you into a material-specific chart in Section 2, Part D, to read factor B. Run B through one more equation, and you get your allowable external pressure. If that's not enough for your actual design pressure, you assume a thicker shell and run the whole chart sequence again. It's iteration by design, not a shortcut you are missing. That length variable, L, is the single most powerful lever in the whole calculation, because it's not the vessel's total length, it's the distance between lines of support. A head counts as 1. A jacket closure counts as 1. And so does a properly designed stiffening ring. Shorten that distance, and the allowable external pressure climbs dramatically, often far more efficiently than simply adding shell thickness ever could. That's exactly what UG-29 stiffening rings are for. A ring welded or braced around the shell purely to create a new line of support partway along the vessel, breaking one long unsupported span into two shorter ones. The ring itself needs enough moment of inertia, essentially, enough resistance to bending and buckling, calculated through its own version of the same factor A and B chart procedure. Get the moment of inertia right, and a few strategically placed rings can be dramatically cheaper than uniformly thickening an entire shell. One more nuance, a stiffening ring doesn't have to work alone. The code lets you credit a width of the shell plate immediately around the ring as part of the same combined section, ring and shell acting together, the same way a flange and web work together in a structural beam. Considered together, that combined section often needs a smaller ring than the ring would need carrying the load entirely by itself. Quick recap, external pressure is a buckling problem, not a stress problem, solved through iterative charts rather than direct formulas. Lines of support set the critical length variable, and stiffening rings exist purely to shorten that length efficiently. Ring and shell can even be credited together as one combined section. That's Season 2, Episode 2. Full chart walkthrough is linked below on WeldFab World. Subscribe. Episode 3 covers corrosion allowance strategy.